Yeah, good evening to all of you. Like we are presenting to the astro informatics project, that is the deep neural network creative. Like what is the creative means? Creative means like styling photo, like allergenic imaginary photo, and even in the productive in the dream photo. Means the totally means the technique of transform image iteratively modify them to enhance the activation of like specific neurons in an deep neural network. Next, like and we divided into project into like three phases. That is the first is the neural network basic architecture, and the second the neural style transfer algorithm, and third is the deep dream algorithm. In the neural style transfer algorithm, like we have used like a VGG 16 model, and the what does this mean? The neural style transfer algorithm, it refers to like class of an software algorithm, and that is the manipulate digital image in also including the videos, like in order to adapt the performance or the visual style of another image. Like neural style transfer algorithm are characterized by the use of deep neural network for the sake of like image transformation. Like the common uses of neural style transfer or the creation like artificial artwork from photograph from like one photograph with including style to form an like artwork. And the third is the deep dream algorithm. We use like ImageNet model in this. It is like an computer visual program that uses like a CNN network to find the enhance like pattern in images like via algorithmic. Thus, it create dream-like psychedelic appearance in the form of villages. Like example, hallucinating dream images. And the next slide. Yeah, the third one is that this is the neural network arch- uh, architecture, and this like this artificial neural network is generally like called neural network, and these are like an computing systems that is inspired by the biological uh, network. And in this model it consists like mainly the vectors and the edges, and in this the connection, the type of the models having the weight that is as adjust to the learning procedures. The learning procedures, the weight update as like an human behavior, as the fact the human learns their experience through their experience, but the artificial neural network learn through mainly through the previous mistakes what it did in the previous. The main relationship between these to the natural and the artificial is the natural is really wonder because it can create artificially with some of the technique. Some things like we can say it is possible for the neural network to identify something seeing earlier as a dream. It is possible with the humans we can create like creative and dreamed. Like example we used in this project like style transfer algorithm and the deep dream algorithm. Let's be seen in the next slide. Yeah, the style transfer algorithm that we used as a VGG network. In this like VGG network, it is before going to that, I will give the explanation about style transfer, because the style transfer, the technique, it is an composing of images like style of other images. In particular, like exploring the possibility to transfer from a normal image through an artistic style from one painting to another through the CNN. Like CNN, it's generally an hierarchical representation from raw images, but with that understand behind the style transfer, in our case, the results that were generated in an VGG16 model. It is one of the top, most top find the accuracy in the ImageNet, and this showed the possibility like increasing the accuracy of substituting like a big filters and including also the small filters like 3 cross 3 as we seen in the image. And there exists like a several configuration in the VGG model, but we can generally say that the convolution stride is fixed to 1 pixel and the padding it is an preserved, where the max pooling is performed like kernel size 2 cross 3 and with stride 2. And in the convolution there are 3 dense layer. At the last one there is an soft max it contain like 1000 channel. Like all hidden layer instead like performing in the non-linear transformation with relative linear unit. Here there is an how VGG network learns that low level feature to possibility to go in the deeper into a network through the convolution layer, represent a larger feature scale, giving like an higher level representation of the image content. And this is about the VGG model, and the next part is explained by Pietro and Alberto.
Yes, thank you, Abhishek. This served as foundations for the style transfer. And now let's take an overview of the algorithm. Basically, the main protagonists here are three. That is a content image that we will call C, a style image that we will name S, and a target image Y. The target image is initialized at random, and the main aim of the algorithm is to iteratively change this image in order to make it similar in terms of content to the content image C, and similar in terms of colors, textures, and patterns, so basically in terms of style, to the style image S. And this process can be obtained basically by minimizing a loss function, L total, that basically is given by the composition of two main losses, a content loss, L content, and a style loss, L style. And basically, we can also tune two parameters, alpha and beta, where more precisely, alpha is tuned to weight in some way the amount of content that must be transferred from the content image C to the target image Y, whereas the parameter beta is used to weight the amount of style to keep from the style image into the target image. In order to better understand the way in which the target image is changed, iteration over iteration, let's go deeper into the details of these two losses, starting from the content loss. So here we have a content image and a random image. And we can define this content loss, L content, as the mean square error between the feature map F at layer L of the content image and the feature map P at layer L of the random image. So basically, we are forcing the activation features of the random image to be as similar as possible to the activation features of the content image. And so the animation clarifies what happens when we try to minimize this function. As you can see, iteration after iteration, all the content from the content image is transferred to the random image. As regards for the style loss, here of course we have a style image and a random image, and we can define the style loss in a similar fashion to the previous one. But in this case, it is a bit more complicated because in this case, we don't deal directly with the feature maps, but with the gram matrices. Basically, here we have the mean square error between gram matrices, where gram matrices in gram matrices, each element is the dot product between feature maps. More precisely, let's say that GL is the grammar matrix of the style image at layer L. So we have that the element ij in the grammar matrix GL in position ij is the dot product between a vectorized form of the feature map I at layer L and the vectorized feature map J at layer L. So we can define in a similar fashion the grammar matrix A also for the random image, and thus it results that the grammar matrices are extracting basically the aspects of the style, so the patterns, the textures, and the main difference with the previous function is that as we have seen here in the content loss, we select a specific layer L. But here, for the style loss function, we select a bunch of layers. Let's say we enumerate them from 1 to capital L. This is because in a neural network, at different layer, we are extracting different aspects of the style in this case. Let's say from larger aspects to finer details. So by selecting several layers, we are trying to extract several aspects of the style. Like I was saying, lines, curves, colors, and so on. So here the animation clarifies what's happening when we are minimizing this loss function. And as you can see, the result is quite different with respect to the other one, because in this case, we can see that the random image is changing in such a way that the colors and I will say in this case brush strokes and shapes are resembling the ones of the style image, but we cannot, the content is not transferred in this case. When we combine the reduction of these two losses, the result is this one. Our random image is initialized at random. We have as content image a picture of Naples, and as a style image the famous painting The Scream. And iteration after iteration, we can see that the random image starts to take from the content image basically the content, its content, so Naples basically, but it is represented with the style given from the screen. And we can show you other results. We have the picture of Naples. We tried it with in the first and in the third example, we tried with different paintings. And this is the result. Whereas in the second example, we tried to transform the photo into a drawing. So basically, we chose a drawing actually as a style image, and I must say that we are very happy with this result. On the other end, we have because actually it's very beautiful, but also it's very interesting the fact that we are actually extracting the style, because as you can see here on the left, we have this tree basically in the image that is not reported in the final image. So it's true, we can see that it's true that we are extracting the style from the image, but not its content. And it's quite impressive. Don't know if you agree with me. And regarding the other example, we have as a second content image, we took this famous portrait, the girl with the pearl earring, and basically we tried to transform this portrait into an abstract one. And so as you can see in the right panel, or better on the left column of the right panel, we selected the three abstract portraits. The third one, a very abstract one. And basically we tried to transform the portrait, as I was saying, into an abstract one, and these are the results. Okay, that's everything about the style transfer algorithm, but we also tried to explore further the possibility for neural networks to be creative with another algorithm that is called Deep Dream. And it's very interesting also from a didactical point of view, as Alberto now will show.
Yes, that's because basically when we have done style transfer, we have just taken two images, one for the content image and another one from the style image. And we have just forced the network to be creative in the sense that we have forced an image to take a content and then to take a style, and we mix that. But what if we want to have a network that is, let's say, creative by itself? So it's just like in dreams. As a matter of fact, while we are dreaming, our minds build up strange things, crazy things. And sometimes we are able in dreams to understand, to create a connection between the dream and what we have just seen. So our past experience and let's say our past learning. So we will exploit this connection between past learning and dreams to build up what is the algorithm known as deep dream. And let's say that deep dream cannot be considered only a way of having a creative neural network. As a matter of fact, as Pietro just introduced, it is mainly a method, an algorithm for model understanding. And let's see why. Basically, deep dream is based on pre-trained neural networks. And after the training phase, we want just to know what the network has learned. So we will ask one or more layers to show us what they have been learning during the training. And that's done in a very straightforward way. As a matter of fact, we fix one or more layer, we take an input image, and we run a gradient ascent on the input image. That will cause, iteration after iteration, a change in the input image, a change that leads the activation of the layers to fire with more probability. So the image, iteration by iteration, will be as close as possible to what the layer has learned during the training. That's just like a backpropagation algorithm, but in that case, the weights are held constant, and it's only the input image that changes on what the network has learned. Basically, the main algorithm and the general workflow of the algorithm is exposed below, and we have based load an original image, then we have downscaled it at different sizes, and starting with the smallest size, we have run the gradient ascent, then we have upscaled the image, and then we have injected the detail that we have lost at upscaling time. We have done this algorithm iteration by iteration until we are back to the original size. And as I've just said, in order to perform this algorithm, we need a pre-trained neural network. So we can go on the next slide, since we have used the InceptionNet. Basically, InceptionNet is a convolutional neural network that, let's say, tries to improve and to get better performances of common convolutional neural network. And that is done by including what is called sparseness in the model. So basically, who developed the InceptionNet tries to get the network bigger, both in depth and in width, but facing two main problems. The first one is the increasing of the parameter space, and the other one is a consequence of it, that is the increasing in the computational complexity. This is, in a certain sense, faced by InceptionNet, including the sparseness of the inception module. To understand that, we can just, let's say, get an overview of the inception architecture. It is based on the first part, that is a stem, and the following part are the inception modules. They are based on the concept that when we are dealing with images, we know that each part of the image has an important part, but we don't know upfront what should be our receptive field on the image. So basically, when we are passing an image in the inception modules, we are convolving this image with different kernel size. So let's say we are just analyzing various levels of details. And in a certain way, we are letting the network to choose which is the right kernel size to understand what is our main problem. And then we have different output classifiers in the inception net as it was built in this way. Then we can go on, since now we have just built our model, we can implement the deep dream algorithm. And the first result is about the creativeness of the algorithm. Basically, in these results, we just wanted to show that it's possible, choosing several layers, to obtain hallucinogenic-like structures. And since the weights of inception net are mainly based on a dataset, a well-known dataset called ImageNet, we can see in this image animals-like structure that act as a mayor, let's say. Another result, as I was saying previously, is about model understanding, and we can see it in the next slide. Here it is. So basically, we have just split the network in three main parts, and we have analyzed the first part, that is the one closer to the input, that is called the module 1, so the first inception module. And we can just see by the results of Deep Dream that the image is changed by taking only the low-level features, so straight lines, horizontal and verticals, but basic, simple types of structure of features. On the other hand, when we are going to the next steps, and so when we are going deeper into the network, we can see more structured information. And as a matter of fact, in that case, we can also distinguish some patterns that everyone can see. As a matter of fact, if you can zoom on the veil of the girl, we can see a dog right here, for example. And then instead, if we move on, also going deeper and deeper, we get an image that instead is a combination of high-level features. And so it's too difficult to find a visible pattern, since the information is so intricate that it cannot be seen as simple as in the module 3 and 5, for example. These are our results, and this is all about Deep Dream. So thank you for the attention.